Okay, so I got it to stop glitching. So again, the formula we're using is energy equals Planck's constant times the speed of light divided by our wavelength. We just converted our wavelength into meters. So now what we need to do is, let me do a smaller one here. We're going to do Planck's constant. It's actually 6.626 times 10 to the negative 34. We're rounding it up to 7 so it's easier to calculate, because we're not using calculators. Why is it doing that? Okay, so 7 times 10 to the negative 34, and that is joules times seconds, times the speed of light, which is 3 times 10 to the 8th meters per second. So I'm going to go ahead and draw my line and put my seconds in the denominator. And then the wavelength that we just calculated, that is 3.5 times 10 to the negative 7 meters. So immediately if we're looking, we can see that the units that cancel are meters on top, meters on the bottom, seconds on top, seconds on the bottom. That means we're left with joules. That's good because that's how we measure energy. So we know we're on the right track. All right, so let's be strategic in how we solve this. Let's do it in parts. So let's do 7 divided by 3.5. So that's going to be 2. And that's going to be 2 times 10 to the negative 34. I'm going to do it in parts. Times 3 times 10 to the 8th divided by 1 times 10 to the negative 7. Okay, so now that we have this, obviously the coefficient 1 is fine. So we're going to multiply our coefficient. So 2 times 3 is 6 times 10. Let's do our negative 34. If they're multiplying the exponents, we're actually adding them, plus 8. And then if we're dividing an exponent, we're actually subtracting it. So minus a negative 7. So that is, I'll do a different color. Negative 34 plus 8 is a negative 26, plus 7 is going to give us a negative 19. So our answer is 6 times 10 to the negative 19. And remember what was left was joules, because we're calculating energy. A lot of brain math on that one. Okay, let's do this next one. Again, it says it's gigahertz. That's frequency because it's hertz. But the problem is it has to be just hertz. It can't be giga or pico or milli, anything like that. So we need to convert our gigahertz into hertz. So gigahertz, we've got 10 to the 9 hertz is equal to 1 gigahertz. Let's move that decimal over twice. So that's going to be 4.23 times 10 to the, going that way, 11 hertz, which is also a per second, right? Okay, so now that we've got our frequency, we don't need to we don't need to use the equation that we used here because we have frequency. And so we can use the equation E equals energy of a photon equals Planck's constant times frequency. So again, we're using the number for Planck's constant, 7 times 10 to the negative 34 joules times seconds times frequency, which we just figured out. And remember, it's either a hertz is a per second, so those equal to each other. So that is going to be 4.23 times 10 to the 11, and I'm going to go ahead and put per seconds, Well, what do you notice? I have seconds on the top and I have seconds on the bottom. So those cancel. So I'm only left with joules, which is good because that's how we measure energy. So can we just call this 4, since we can do it in our head? So 7 times 4 is 28 times 10, and we're multiplying it, so we're going to add those exponents. So negative 34 plus 11. So that's going to give us a negative 23. But we're going to move that decimal over 1 so it's in correct scientific notation. So let's do 2.8 times 10 to the negative 22, and our units are joules. That's our energy, the units that measure energy. All right. The last one on this one, it's at the top of on the back of the page. We're back to wavelength, but we're not in meters, so we've got to convert those meters, centimeters into meters. So let's do that first. So centimeters, that is, let's see, there's 100 centimeters. So if we do that, that's going to be 10 to the negative 2 meters in 1 centimeter. So let's put that in correct scientific notation. 1.2 times 10 to the, well, that's easy, negative 1 meter. And I'm going to do it like this so that it keeps it with scientific notation and it's easier to kind of put it in there. All right, so because this is wavelength, we have to use the combined equations. So remember, that is energy equals Planck's constant times the speed of light divided by wavelength, lambda. All right, so Planck's constant, 7 times 10 to the negative 34 joules times seconds times the speed of light, which is 3 times 10 to the 8 meters. And let's go put our per and seconds underneath in that denominator. And then our wavelength that we just converted from centimeters to meters, put that in the bottom. So that's 1.2 times 10 to the negative 1 meters. Again, if we look at our units, meters on the top, meters on the bottom, seconds on the top, seconds on the bottom. All we have is joules left. That's what we're solving for energy. So we know we're on the right track. Okay, so let's do it this way. How about, instead of saying 1.2, let's just call that 1. So that is going to be, well, I like dividing by 1. So 7 times 3, 7 times 3. So we're going to get 21 times 10. We're going to, since we're multiplying those exponents, we're going to add them. So negative 34 plus 8. And then we have to subtract if we're dividing those exponents. So minus a negative 1. So we get negative 34 plus 8, that's a negative 26 plus 1. So that's a negative 25. So our answer is, do I have space? I don't know. 7.3 times 10 to the negative 25 joules. There we go. Oh, no, not 7.3. Oh, this is when I need to have you guys in front of me. No, 2.1. Oh, but that, we move it over 1. So that's got to be 24, doesn't it? Yeah, no, that needs to be 24 because we moved it over 1. Sorry. Okay, so that is the last of our equations. Let's look at number 4. Order the following types of light from most to least energetic. So we have 10 to the 6 hertz. Remember, that's frequency. 10 to the 6 meters, that's wavelength. 10 to the negative 6 meters, that's again wavelength. 10 to the 26 hertz, that's frequency. 10 to the minus 10 meters, that's wavelength. So he says this can be done with 0 calculations and to justify our answer with words. So we're going to talk it out. So one of the ways I did it, so we're going to do from greatest to least, and I'm gonna list them here so we can actually see it. So our frequency, we have 10 to the 6 meters, wavelength, oh no, sorry, not here, meters, hertz, and then 10 to the 6 meters, and then 10 to the negative 6 meters, and 10 to the 22nd hertz. Oh, and 10 to the negative 10 meters. Okay, so remember, our relationship between energy and wavelength and frequency is as energy increases, the frequency increases, but our wavelength decreases. So we want that to be the case over here. And then the lower the energy, the lower the frequency, the higher the wavelength. So obviously we've got, let's see, the highest wavelength is this one. That is the highest wavelength. That's going to be the lowest energy for sure. So let's put that, well, there's 5 of them. So let's just number this. This one's going to be 5. The one with the highest frequency, which would be the highest energy, is going to be this one. So that's going to be number 1. And it looks like we've got 2 that are kind of seem to be in the same area. But neither of them are going to be as big as this one. So 10 to the negative 10, that's a really short wavelength, so that's going to be our second greatest. So then we need to kind of look to see between the two. So remember when we were converting, or we were solving for energy, and we had frequency, that is just times whatever that frequency is times Planck's constant, so 7 times 10 to the minus 34. But when we have wavelength, it is Planck's constant times the speed of light divided by the wavelength. So because you have that Planck's constant times the speed of light, that's going to really increase what that energy is. So this one, the 10 to the minus 6 meters, is going to be our third most energetic wavelength, and then that would mean that this one over here is number 4. Yeah. So the greatest is going to be 10 to the 22nd hertz, and then it's going to be 10 to the negative 10 meters, and then 10 to the negative 6 meters, and then 10 to the 6th hertz, and then 10 to the 6th meters. They use all those same numbers, kind of get confused there. All right, so again, if you need to prove it to yourself, you can do it with some calculations and just solve those for energy so you can see what the math is actually doing. That would make that energy get higher. All right, so then number 5, from memory to the best of your ability, reproduce the electromagnetic spectrum, starting from the most energetic types of electromagnetic radiation to the least. You must use a diagram and your own words to answer this equation, or this question. So we want the highest to the lowest, right? there is a video that I have put onto this assignment, and it's called the Electromagnetic Spectrum Song. And so I want to make sure that you watch that, I'd say at least 2 times, and we are all going to be singing that together. You can use the subtitles, that's fine. But make sure that you can sing it, because I'm going to walk around, and if people don't sing it, then we'll have a nice solo. Like they can stand up on their chair and do a solo. It's so much fun. All right, so anyway, the song, and because I know this and know the song, I have no problem remembering the order of these. They actually do it in the song lowest to highest. So I'll do it that way, and then obviously you would just have to transpose that. So the lowest is radio waves, and then we have microwaves, and then infrared radiation, visible light, and then ultraviolet, and then X-rays, and gamma rays. And if you sing it enough, you'll start to sing it on your own. Then you know you've got it. You need to know the order of those. And we will add more to that as we talk about all this later. All right, so that, I believe, is the end. Please feel free to go back, put these 2 together. And then if you have questions, please write them down. You can email me or write them down, and we can talk about them on Tuesday, but I suggest emailing me, and we can get that taken care of quickly. All right, so move on with the rest of your assignment today, and I will see you later. Bye.